share my screen. So just to preface this a little bit, I'm actually just 6 kilometers away from you all. But I woke up yesterday with a sore throat, so just to spare everyone else the possibility of also getting a sore throat, I'm doing this from our lovely hotel, which is close to the Space Center. So, okay, can everyone see my slides? Yes, I think so. Okay, good. Perfect. Okay, so I'm going to be talking about the new head echo analysis algorithm we've developed and some applications on the new radar that we've done. So starting off, as Gunther showed, we can have the radar meteor head echoes measured by the radar system like this. So we are looking at the dense region of plasma around the ablating meteoroid instead of the trail echo. I'm not gonna explain this any or to talk more about this now. Let's see, where is, I lost some parts of my screen. There, now I have it. Okay, so motivation for why did we want a new analysis algorithm? So basically, we had some scenarios in mind that we wanted to look up and try to do studies on. So one of the example scenarios was a history model. So let's say that we analyze some radar data, we see the meteor head echo, we derive the meteoroid parameters in orbit. When we after we've done that, we want to see what was the possible histories of this meteoroid. So looking at a single event, going backwards in time, and then maybe, for example, associating that to a parent body. And having the uncertainties when you do that is very important. And having a probability distribution is even more important if you want to look at the possible histories that you can have. Another example scenario that we wanted is stream modeling. So you would model the meteoroid stream, you would propagate the stream forward in time. So this is, I guess you can see my mouse? Yes. So this would be this path rather than this path. But then we want to predict and model the detections that the radar system would have made of this simulated meteoroid stream. And then also compare what the simulations gave us to the measurements. And both of these scenarios rely heavily on having instrument functions, so having the bias functions or observability function of your instrument. It relies heavily on having very, very accurate uncertainties of your measurements and being able to look at individual events. And talking about individual events, here I made a sort of sample thing where you have a nice distribution. This is just to explain the point. So you have this nice distribution, and then you have these points here that are just outside of everything. So we wanted to reliably investigate individual events. And then you can say, well, this is a bug, and you flip the table and you have to fix your code. You can say that this is an outlier. That's interesting because that means, or what I call it is that it's basically something that is not supported by the models in your analysis. And then you can have things like this that have high reliability and everything. Your models fit it perfectly. So maybe it's something new. Maybe it's something that isn't explained by this regular distribution. And that's interesting. So this was really the goal that we wanted to get at. So to get to that goal, I had a small to-do list of one task, which is to go from data to model fits with realistic uncertainties as probability distributions, and then add in proper calibration, validation, and simulations. That's just one item. That's it took a while. And then, of course, to do the other parts of the scenario, there are more things to do. So far, I've only gotten to this measurements part. This is future me's problem. These 3 dots here. So we applied this new analysis on the MU radar in Shigaraki, Japan. It's 475 antennas spread in a field that's approximately 100 meters in diameter wide. The important part is it has it collects these antennas into 25 receiving channels, so we can do very good interferometry with it, and actually get out, even though it's a monostatic system, we can get out very nice meteoroid trajectories, and I'm going to show you more about that. And also Johan will show more about that in the next talk. So some of the design, how did we build this new analysis? So to reduce the computational time, we have an event search algorithm, which just goes through all the raw data, flags whatever it finds as coherent echoes, and then categorizes them if it's a head echo or trail echo or something else that can't be identified. This is also really good because this, when you have filtered out all the coherent echoes, you know what is the background of your data, and you can use that to estimate noise parameters and use it for calibration later down the line. And then we have the signal analysis. If anyone is interested in how we do the signal analysis, maybe if I'm healthy by tomorrow, I can actually join, and we can talk about it afterwards. And then the important part for the uncertainties is this Bayesian fitting, which is the new method that we had to figure out the Meteor model parameter distribution. And I'm going to talk more about that now. Yeah, and of course, then we also have a results crawler that makes it all into a summary database, because each individual event is a time series and it has lots of data. So when you want to compile the summary database, of course, you want to simplify the data somewhat. Okay, so model parameter estimations. Basically, what we did is just take Bayes' theorem straight off. So for those familiar, you know that here we have the posterior, which means basically what is the probability of your model parameter. So this model here, that's the parameters of your model, given your data. And that basically tells you what's the distribution of possible models that fits the data well. This is the probability of the model. That's called the prior. Since we don't know anything about the meteoroid before it hit the atmosphere, this is flat. This probability of the data, that's just a constant. Ignore it. So what's left is this thing, the probability of the data given the model. That's called the likelihood. And to generate the likelihood function, you need to have a very good grasp on the uncertainties of each individual data point in your time series. So to do that, we ran a massive amount of direct Monte Carlo simulations, where we generated raw data, noisy raw data, and had a coherent target at all possible ranges, all possible velocities, all possible positions in the antenna gain pattern. Now I say all possible, but a range, a sensible range, and a range of signal to noise ratios. And then we let this run for a very long time and built up a cache. So when we measure something, we can take this cache of simulated raw data that's also been analyzed by the same signal analysis that we use on the real data, and say, oh, this is the predicted uncertainty. So if I go to the lookup here and say that for a range of 135 kilometers and a velocity of 50 kilometers per second, and I had an SNR of 20 dB, this is the sigma that I would expect. And then also when it's at this place in the gain pattern, this is the uncertainty I would expect in interferometry. And there was a lot of tuning involved, figuring out what error sources we actually had to get this cache to actually fit the residuals that we see when we do our fitting, because that's the important part. You can't just do this and expect it to work. You have to actually validate that your simulated measurements error match reality by looking at the residuals after your fit and see that they actually well predict what you see in the data. And when they don't, you probably have found some interesting new aspect of either the phenomena or something happened with your instrument that you didn't expect. And that's also good to find out. Some other upgrades that we did, we are looking at model matching levels now, which was very key to the first study that we did. So we actually make sure that the interferometry found a good match, because when you run interferometry solutions, you will get the solution even if the match is really bad, because the algorithm just says get the solution. The same with the range and range rate decoding the signal, you just always get the solution. So now we are also having a very strict demands that the matching level will have to be good. The plug and play Meteor models is an important part, because that means that we can put in simpler meteoroid models, just a line with exponentially decaying velocity, for example, or we can put in a full-blown ablation model and try to fit the data to that instead. We have some signal processing, orbit determination, and modern software design is something I will come back to at the end. Okay, so some results. This is how a typical event looks. So here you have a range time intensity diagram. And this block of increased power is the received radar code. So these red lines were put in by the event search. It said that here's an echo. This is what should be analyzed by the entire pipeline. Here we have a ground projection of the track. So this is in east-north units in kilometers above the radar.
Okay. Daniel, you have 2 minutes.
Yes. Okay, so let's see. Yeah, and we have exponential velocity. So actually, the full screen removed my clock. That was why it went a bit slower. I'm sorry. Okay, so when we run the Meteor, the Bayesian fitting, this is the kind of distributions that we get. Actually, now just yesterday I improved this a little bit, so we get better samplings now. But this is all the model parameters of the meteoroid model, and you get this distribution. This is the probability distribution of the model. And then you can look at what is the 3 sigma distribution of velocity, for example, and you get this sort of range for the 3 sigma interval for velocity. And then this also, of course, translates to a distribution in orbit. So here you see semi-major axis versus eccentricity is this narrow curve here. And now we're in, you see, this is very close to 1 eccentricity. So this is in outlier territory, which is why the old analysis has such a different value than the new analysis, because here the individual uncertainties of the data points really do matter a lot. Yes. Okay. So high altitude detections. This was the first case study that we did. So we looked at these events that were very high altitude compared to the regular ablation theory. The interesting part, most of these in the high range were removed by bad interferometry immediately. They were just gone. This clump here was due to a problem with the signal analysis before. So now with the new analysis, all of these dots in the old database move to these new positions. So this was 305 events out of 106,000 survived in this high altitude regime. So it's not a lot. Only 4 events were above 145 kilometers. So that's like very, very few. So if we look a little bit about the material composition, just the first order look is this KB parameter. And pretty much all of these are classified according to that as soft commutator material. Now this is just the first order check calculating this. And what remains to be done is looking at these more thoroughly and figuring out what makes them ablate at such a, or produce an echo, I should say, at such a high altitude. Okay, I'm going to skip this. And just the final one, there was this manual correction that you saw. And that's just because the event search basically tells me that you are not allowed to use this part of the echo because it's too unreliable. So I just manually take this red line and draw it back here because for these high altitude events, I wanted to look at the full thing. So that's the only manual correction I did. And I'm going to finish on the fact that we're trying to publish everything open source now. So if you want to try what we're doing, look at my GitHub, download, make issues, tell me where the bugs are, it helps. And maybe we can reduce the amount of work that we all do. So thank you.